Dear listeners, welcome to the second part of the online international workshop, Differential Equations and Interdisciplinary Investigations. I present to your attention Professor of the University of Leicester, UK, Director of the Center of Artificial Intelligence, Data Analysis and Modeling, Alexander Garbany. He will give a course of lecture, Data-Driven Artificial Intelligence, Problems and Ideas. Dear listeners, I remind you that if you have any questions during lecture, you can write them in questions and answers. I will read them at the end of the lecture. Professor Garbany, you are welcome.
Hello. Everything is fine? Can you listen to me? Hello?
Yes,
yes, everything is fine. Just first technical question. So it's my great pleasure to be here today. I will present you today non-technical review of the main problem of current AI, data-driven AI. Of course, you know that AI systems have two generations, knowledge-based AI and data-driven AI, and now everybody speaks about neural networks, machine learning, and so on. And I will also speak about data-driven AI, problems and ideas. This is partially my keynote talk from the World Congress of Computational Intelligence this summer. Okay, just to introduce myself, I started my travel in neural networks very early in 1990. These are some books and a special diploma of special award of pioneer of Russian neuroinformatics. Now I work at the University of Leicester, Director of IDAM, Center of Artificial Intelligence, Data Analysis and Modeling. So the first problem today is a problem about the problem. We'll discuss which problem do we have. There is a Gartner hype cycle, how innovations live in our world. After start, each big innovation goes to the peak of inflated expectation. You can see here this peak. But then after some time on the peak, it drops down to a big, down the hill. And now artificial intelligence is in this motion. We are going down in the process of de-illusionment. Then after that, there is expected a way to plateau of productivity. But maybe as it was happened with neural networks, with artificial intelligence, again, new peak, new drop down, this will be artificial intelligence winter, and maybe some periodic oscillation will follow. I don't know the future. But what problem will push us down the hill? What is the main problem that pushed us down and pushed us down many times before, at least 3 times? We had this process already 3 times. Maybe the same problem that was pushed us down many years ago. I try to answer these questions about problems and give some ideas, not the answer. I don't know the answer, but give some ideas. In mathematics, this is a long tradition to discuss problems, and this discussion moves us ahead. At the beginning of 20th century, David Hilbert started this representation of problem and pushed mathematics and focused attention of mathematicians for many years. And even now we are continue to solve Hilbert's problem. Marvin Minsky posed main problems for AI in 1961. Marvin Minsky is one of the famous father of data-driven AI. He selected 5 main problems: search, pattern recognition, learning, planning, and induction. These problems, this famous work focused at researchers, and we can see great success in all directions. Well, let's go to Marvin Minsky definitions, not in detail, but to understand this problem. Search. If we have a big problem, massive problem, and we can test is some example solution of not or not, nevertheless, we should find the trial solutions. We should look through the huge number of possible solutions, not randomly, not by selection all possibilities, but very important directed good solutions. Like, there are famous examples in numerics like simplex method, gradient descent, and many other for optimization and for other, I should not list, but that any device that gives us good search will add great value. This any device. And of course, very nice example are Google search, Yandex search, many search, Amazon search, many search engines are now online. This is not the whole world of search, but it's a good example. Pattern recognition. Pattern recognition, everybody knows the best example is face recognition, great success of neural networks. With some questions, of course, but definitely now face recognition is not worse than human face recognition, automatic face recognition. And learning how to solve new problem. There is one difficulty that Minsky focuses there. Distribution of credits and responsibility for errors. Each complex decision involves many steps and many assumptions. And when you succeed or fail, we should know which step in decision is responsible. And this is, in successor reinforced decision models, is very difficult to decide. And this problem, of course, we have now some ideas and tools, but this problem exists. Planning. Solution of complex problem. If you solve a complex problem, you need. And you should split the problem into sub-problems. And this split and administration is huge problem. And now we have, of course, we have many tools, but this problem we continue to solve. And induction. Induction is not so well solved problem as everything else. Induction is the creation of deep explicit knowledge from data. And this, of course, if this one step in depth, yes, it's possible. Decision trees and several steps in depth. But really deep induction is very difficult. And one of the main machine learning problem is data-based AI problem is extraction of deep knowledge from data. For example, extraction of general relativity from very simple data available to Einstein. Einstein had not so much empirical data about gravitation. He extracted, he understood that should be general relativity very deep theory. This is just an example. Exercise. Now I can propose you an exercise. If you like to study artificial intelligence, very simple, sound. Read the paper of Minsky. Please read. I cannot, we can read together, but this will be another lecture. Then find the main latest achievement. Just go to Google Scholar and by keywords find the most important reviews of last decade. Not so many, most important review papers. write a mini review of these reviews, of these achievements, and compare the modern situation to Minsky ideas and hypotheses. After that, you will have a very good impression about current state of machine learning and data-based AI. And this exercise is not like a 1/3 of master thesis, just introduction to master thesis. It's not, or maybe by some sort of undergraduate coursework. It's not so much, but this is extremely important to do such a work once for a student, if you like to work in there. Okay, now a mountain of success of neural and AI inspired us. And I should say that during last years, maybe 2 decades, like 2 million papers about neural networks were published. However, 2 pebbles are in our shoes, 2 small stones are there. And these small stones can slow down our fantastical moment. First, it's very important, AI makes unexpected mistakes. And AI will make these mistakes in the future. If you have a data-driven AI, it will always make a mistake because because many reasons. We'll discuss a bit later. And the second stone is decisions of neural AIs are not transparent. And therefore, we cannot explain them explicitly. No explicit explanation, no logical explanation. This is very difficult. And the value of these decisions without explanation is not so high as it could be. Okay. The main problem, as I think now, is in unexpected errors. First, the mistake can be dangerous. The first person killed by AI, self-driving machine, was well known. Uber machine killed a pedestrian. Yes, this is dangerous. The second problem of unexpected errors, for example, this Tesla electric car, self-driving car, who is responsible? The driver, the autopilot, the pedestrian, I don't know. So many possibilities of responsibility, and these decisions of AI, distribution of responsibility is very difficult. Okay, so this is unclear who is responsible for these errors. Then, famous example of AI error, facial recognition for detection of criminals. The database and found like possible criminals without reason. 2,000 people were stopped for police investigation as potential criminals because errors of this facial recognition system. Of course, people decided to discuss is it proper number of errors or too many errors. Nevertheless, 2,000 people were stopped, and this, we should correct such a system immediate, non-iterative. We cannot, after each error, explain, retrain the whole system. We need correction of this error. It's impossible now. And again, famous example, IBM Watson. IBM Watson claims that they will be a best cancer diagnosis and treatment advisor machine, and they failed. For example, University of Texas spent 62 million for this system, and read are errors. Errors means errors. It's worse than this usual just doctor, not genius, just standards, much worse. Why? Because they change the model and change the data flux and correct some errors, correct some decisions, but this correction, these new things damage existing, I don't know. The detailed analysis is still not published. And the final, this list of many errors, and I don't like to discuss all of them. Well, some of them are just errors of problem statement. From the famous racist bias, it's just not an error, just an absolutely predicted result of the problem statement. If you take all people in prison in states, and you will find that there are more black people, of course, the percent of black people there is much higher than the percent of black people in the population. And therefore, this simple statistical decision that a black person is probably more, it should be more suspicious, looks more suspicious. But this is racist bias, and now people definitely decide that this is inappropriate. Therefore, I should just state the problem in a different way. And there's some other, Alex, some even in the night, the Google companion said, ha, 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 in the night. So, and the most important, theoretically important problem is the real world is not a good IID sample. And we cannot apply all the statistical estimates or the statistical learning theory to the real world examples, because the flux of events in the real world are not an independent, identically distributed sample from a good probability distribution. Then the fundament of origin of our errors. Well, of course, there are some routine software errors, unexpected human behavior, non-intended use, if you use a system is not trained for it. But there are two fundamental reasons. First of all, uncertainty in training data. If you would like to be certain for 100 attributes, I mean 100 binary attributes, yes or no, plus or minus, that for the complete sample, you need 2 power 100, more than 10 power 30 records for completeness. Of course, we will never have such a set. This is the first. Uncertainty in training data is always present in our data training set, because our training sets are small. Really. Even huge are small, millions are small, billions are small. And then uncertainty in the training process, because the neural network can have different solutions. If you start from another point, you will have different, perhaps maybe the same, maybe different. You use some stochastic elements in training. This is uncertainty in the training process. And errors are unavoidable companions of data-driven AI. Because many reasons, and because two unavoidable reasons: uncertainty in training data, uncertainty in training process. Therefore, the message number one: the main AI problem, errors of AI and their processing. What to do with these errors? And I should say that if we will not solve this problem, then a new AI winter will come. And again, we'll say, oh, AI is something we shouldn't speak about. Let's not pay much attention, and AI will survive. It's only in applications where errors are not very dangerous. I don't like this prediction. I prefer not. I prefer to be wrong. But unfortunately, my experience, I have seen 3 AI winters, and I know how it appears. It's this process. Then what to do with error? So as you remember, I told that there are 2 problems. The problem is twofold. Existence of errors, it's unavoidable. And the second problem, what have we to do? What can we do with these errors? It's the first question. Of course, we just correct, systematically retrain. We can teach the system, we can just take errors, go to the computer, correct errors, and after some time it will return corrected system. But to preserve existing skills, we should use the whole set of training data, because we should not damage the existing skills. And this approach requires much resources, because if you use millions, like for example, face recognition, millions of faces, then retraining requires much resources. Nevertheless, new errors may appear. The preservation of existing skills is not guaranteed. You retrain, test, and probability of a skill damage is a priori unknown. The last sentence needs explanation. No, we studied probability theory, we studied the theory of statistical machine learning, we know brilliant works of Wapnick, we know many things. Why we cannot predict the probability of skill damage? And here I like to review the famous lecture, Millennium lecture of Danoha. David Danoha is very well-known researcher from Stanford in statistics, signal processing, artificial intelligence, and related topics. He told in his lecture was this Millennium lecture. He will try. He will and tries it now. He tried to be like Hilbert. He tried to focus attention on the main 2,000 plus problems. And he told that the number of attributes now is very often much more than the number of examples. Because we automatically measure many attributes in medicine, in space. We use many sensors. We use many automatic systems for data collection. We can measure many things. And usually, for example, I meet doctors. Doctors tell me, we have much data. For each patient, we have 10,000, 20,000, 30,000 values. Okay. How many patients do you have? How many people? Like 30, 60. You see, 60 people in 10,000 dimensional space, 60 points is nothing. It's just. Danoha says this is the number one problem. The number of attributes is much bigger than the number of examples. And he calls this world post-classical. It's very different from the classical world. In the classical world, we have the classical law of large numbers, central limit theorems, and so on. But the number of examples goes to infinity, while the number of attributes is fixed. And these results have, don't fail. He says fail, but have no sense for post-classical world. These results cannot be used when the number of attributes is bigger than the number of examples. And he stated that the number, this case is not an anomaly, this is generic case. You can find this lecture online. Thus, the classical statistical learning theory is mostly useless in the multidimensional post-classical world. Like each broad, so bold statement can be corrected, and the Danoha statement can be commented, but this comment makes this statement even more important. All the geometric, blessing and curse of dimensionality effects appear already when the number of attributes is much bigger than the binary logarithm of n, not just n. So this we need much weaker inequality. This post-classical world begins before the number of attributes become higher than number of examples. The non-classical world is around. For example, if we have 100 attributes, you always will be in non-classical world, because we will never have 2 power 100 examples. And this is just a reference to our current paper about this. And the comment 2. And the comment 2 is make us more precise. The number of attributes Danoha is speaking about is not the proper measure of the dimension. Dimensionality of data, of course, if you have equidistribution in a ball, uniform distribution in a ball, this will be in 100-dimensional ball, means the dimensionality is 100. But if you have data distributed on a line, dimension will be 1, even if this line is in 100 or 1,000 dimensional space. Therefore, the definition of the post-classical world is that dimensionality of data set is much greater than logarithm of the number of examples. And this is a special paper, open access also, about measurement of this. Just I signed the most recent reviews. Then the problem is how to cope in the non-classical world. How to cope with these non-classical problems. First question is, the main question, of course, if you have non-classical world, can we return to classics? Yes, sometimes. Sometimes we can reduce dimensionality. And the first method for efficient reduction of dimensionality was proposed 120 years ago by Carl Pearson, principal component analysis. Then independent component analysis, principal graphs and manifolds, autoencoders, methods of the previous century. Huge library of methods and software is developed. And more detail follow in lecture 2 tomorrow. And the somehow dual approach is data augmentation. Instead of each data point, let us take a cloud of randomly smeared data. It's also a well-known tool from 1990s. In some sense, we also return to classics. We artificially increase the number of examples, but keep the data at noise. And many details will be smeared and it could be fine. Sometimes this works. There are some references, and the detailed lecture will be tomorrow. But what to do when the return to classics is impossible? I cannot claim that we can always apply PCA, it will work. No, I cannot claim that we always can make data augmentation, it will work. No. Sometimes return to classics is impossible. And there is another idea, rather fresh idea in this, maybe 5, 6, 10 years, it depends. External device, corrector of AI mistakes is needed. I should say this is not retraining. We keep the same AI device, but we add one corrector, a simple device, of course, simple mathematical device, not compulsory. It's in hardware. They say it's the same hard, just a piece of code. A simple device for correction of the errors. And of course, we can work with you. Everybody can formulate the main requirements, technical requirements for corrector. First, it should be simple. If we should train a huge new neural networks for corrector, it will be the same as retraining. You should not change the skills of the legacy system we correct. It should allow fast non-iterative learning. It should allow correction of new mistakes without destroying previous ones. Okay. That's a summary. This is a scheme of corrector as a reference. We have a device, this green device, inputs, internal cells, outputs. Corrector receives everything and it decides about correction with the modified decision rule. Therefore, this is a binary classifier, should classify situations with correction, which need corrections, from situations that don't need corrections. Miraculously simple devices, Fisher linear discriminants, are very efficient for this purpose in high dimension. This is a sort of blessing of dimensionality, effect. In high dimension, something becomes simpler. Let me recall just as very briefly, what is the Fisher discriminant? Fisher discriminant is separation of data clouds. Is this, you have two data clouds with means and covariance matrices. We have the vector mu2, mu is the mean, minus mu2 minus mu1, the right vector. We have special vector modified sigma 1 plus sigma 2 minus, or it may be weighted sigma, but I write just one of the rules. This vector W, weight vector, and there is orthogonal hyperplane through this. We are talking to this vector. It's a linear function. Wx is C is hyperplane, more than C1, less than C first class. More than C. This is the standard scheme of Fisher linear discriminants. Everything is here. You can take this formula and go on programming. Of course, you can change coordinates, and this will be even simpler. The procedure of whitening. Perform whitening. Linear transformation, after that, the covariance matrix becomes identity matrix. Take principal components, normalize coordinates in principal components to unit variance, and after whitening, this weight vector is just difference between mu1 and mu2, and this Fisher discriminant is orthogonal to this difference. After whitening, we can see here absolutely simple. Just center of mass of the clouds and the hyperplane perpendicular to the center of mass, but in U coordinates, not in those. Now, Fisher discriminants are explicit and non-iterative classifiers. Now let us define, for our purpose, I will give one theorem. A point, let data set be centralized and whitened. A point is Fisher separate from a finite set, if this inner product xy is less than alpha xx for all y from data set. This is the illustration. This is x, this is y divided by alpha, this is a vector, radius vector of x, and this perpendicular should be between, should be not further than x, should be here somewhere, or maybe even opposite side of C. That's all. This simple discriminant effectively separates mistakes from the correctly solved example in high dimensional. Why? This is a miracle. I guess let's be a bit more explicit. Okay. This is the theorem about. And this is the theorem. Assumes that the probability distribution has a density with maximal value bounded by this geometric progression. Or let the number of points is also bounded by geometric progression with where n is the dimension. And this important simple equality holds. Then the probability that a random point is Fisher separate from the finite set. You see, finite set should not be random, just a finite set. Goes to 1 as geometric progression. 1 minus geometric p is 1, probability is 1 minus geometric progression. This can be just very simple. This is unit ball. These are balls with excluded volume where x should not be belong. These balls exist for all points of y. The volume of this ball is less than the volume of the big ball divided in 2 alpha power n. 2 alpha is more than 1. Then this joint volume is geometric progression. Decays the fraction of this colored volume. Decays as geometric progression. And then x with high probability is outside. So, extreme points in high dimension. Of course, this is this idea of extreme points. Extreme point is point separable from all other points by hyperplane. In high dimension, with high probability, even in an exponentially large random set, all points are extreme ones. For example, 100 dimension at m less than 2.7 million, the set of my m random point is Fisher separate each point, not one, each point from the rest with probability more than 99%. That's enough. This was invented in statistical mechanics by Gibbs and then developed by Levy, and the blessing dimensionality is a manifestation of the concentration of measure. And all the statistical physics is based on this phenomenon. Reading material. This is concentration of a volume in a ball. Let's go ahead. Plenty of generalization. We will not discuss generalization now, because this, I hope that this representation will be delivered to you. You can just go and look on them. Plenty of generalization, but these two heuristics. No heavy tails of the probability distribution, and the sets of small volume should not have large probability. With small, large, different. In these cases, Fisher discriminants work. Plenty of generation for classifiers, kernel classifiers. Ensemble of correctors with clustering covariance, not for one error, but ensembles. Cascades of correctors when the system with corrector is a legacy system and we add new corrector. And interiorization of knowledge. When we collect many correctors, we can teach the system to interiorize all the corrections. Now we have new big training problem. It's not just one error. We should go to data and to learn. And this is with generated data, labeling, the system with characters can be used for labeling data, and the system will learn with this labeling data very quickly, very fast, very efficient. And this is a way to delete the technical debt and the incorporation of knowledge into system inner structure. Internalization will be organized, I told you, as supervised learning. They use the system with character as a supervisor. Message 2. In the non-classical world, we have a choice, either to return to classics or exploit the blessing of dimensionality and create one-shot characters. Of course, there are many other messages. For example, when the AI can play with the eye, then the progress is much faster. Characters are tools for one-shot transferring skills between deep complicated AI and simple AI, teacher AI and student AI. And teacher comments will be, teacher corrections will be implemented as characters. It's good experience with just with industrial system. And there will be multi-agent systems. Multi-agent systems can implement characters for their purposes, and for each problem the agent can evaluate his level of confidence, and they learn to be not too confident in their mistakes, and then can implement new training with cooperation, coordination, conflict negotiation. This is a principal scheme in the neuroanalyzing community. The agents correct mutual correction, then go and train for incorporate new knowledge and go again. This agent can learn a long time without human supervision and with internal labeling. Not forever, but for some time. Message 3. After tomorrow, AI will be a large social system of heterogeneous AI networks. To meet the after tomorrow future, we have to move from the individual systems to the communities of systems. They collaborate and teach each other. Multi-agent AI. And the character idea and basic of dimensionality will work there. And then, when explainability of AI is needed, about this explainability, we will speak in the third lecture. It will be more technical lecture. But just one lesson from the practice. Users prefer one-button solution. Users not always use the neural transparency. Not use the logical transparent option. This is a fresh preprint with review of the old works. 3 messages. Errors are unavoidable. And the main problem is the errors and their processing. Non-classical alternative. In the non-classical world, we have a choice as a return to classics to exploit the blessing of dimensionality and create one-shot correctors of errors. And the message 3, after tomorrow AI will be a large social systems of heterogeneous AI networks. Explainability is needed. Later we'll discuss this in detail. And if you don't solve this problem, new AI winter will come. Some references, classics, Gibbs, Levy, blessing of dimensionality, Rosenblatt, Talagram, Gromov, Danocha. Some more, Kainen, but not so famous Professor Kainen, who invented the notion, the blessing of dimensionality. Kainen Kurkova also blessing, Baranov, Uredi, Jacobs, again Danocha with Tanner, no, and some, and large review, not only our open access large review. Some our preprints, of course I should advertise my works, and our team. Our team, I like our team, head of systems biology of cancer institute, Andrei Zinovik, Ivan Tukin, Jimmy Lipsley, Evgeny Mirkes, our PhD students, industrial partners, Des Chaim, the former president of International Neural Network Society, Daniel Prokhorov, another former president, Donald Walsh, brilliant mathematician, twice world champion mathematical Olympiad Bogdan Grichuk, and so on. Thank you. Question, please.
Professor Garbani, thank you very much for your very interesting lecture. I guess everything was clear, but the audience have some questions.
I will be absolutely happy if you have time.
The first question is, on your opinion, what would be the most bright example of the application of artificial intelligence to the mathematically formulated problems?
So I should answer as it's now in community. In community, many people try to apply artificial intelligence to computational proofs of theorems. Computer proofs of theorems. The success is still very modest. But many people hope, for example, our friend and co-author Bogdan Grichuk likes this problem and works on that. If this will be important, if we achieve this result. I'm not enthusiastic in this direction. That's all. That's all. So this is the main attempt. There are many other trials, but this is the main.
Okay, thank you. The next question is, can you convert these general dimensional rules into recommendations regarding relations between the number of layers of ANN and the number of input parameters?
Number of layers, number of input parameters, there is no relation. I should stress that there is absolutely no relations because everything depends not on the number of input parameters, but on the dimensionality of data. And the first advice is analyze the distribution of data. Then analyze the dimensionality not only on the data, but on the problem. Some problems are very simple. For example, you can just project the data on one principal component, maybe not the first, maybe second, third, and find that classification is perfect if you solve a classification problem. This is a dialogue. There is no advice. But advice is analyze dimensionality. Second, try simple dimensionality reduction and 1D, 3D, 2D separator rules, and then go ahead. And there is no moreover, I should send to our preprint, maybe it's here. Mark Mirkis graduation. How deep should be the depths of convolutional neural networks? We just followed this idea. We just use it, the standard problem, recognize friend of for people, for faces, and analyze how deep should be the depth. We find that say 5-7 layers will be fine, but usually people try to use 17 or more. And this is just case study. It's not the whole technology, but the case study. Okay.
Okay, thank you very much. Unfortunately, we didn't have time to discuss all the issues. They can be discussed at the discussion in the evening. So thank you very much for your lecture again. We are looking forward to your next lecture. And dear listeners, a break is announced until 4 p.m. in Moscow time.
So, Nick, may just one comment for students.
Okay, of course.
Brief. So tomorrow, I will please keep your questions for today's lecture for tomorrow. Tomorrow, I will leave more time for questions, especially. Please create your questions and keep it until tomorrow. Fine?
Okay.
So especially today is just non-technical introduction. Tomorrow will be more technical.
Thank you very much.
Thank you for your attention.
So now we'll have a rest.
Okay, bye. Thank you. Okay.
Ok. Il y a quelqu'un qui me... Oh, j'ai ramené du son. J'ouvre ça. Partager, Olivier.
Non. Annulé.
Microphone should be on. Okay. Okay, the mic, I don't touch anything. I put it on full screen when you want me to talk, okay?
Dear listeners, welcome back to our workshop. Our next lecture, Professor Bardos. He will give a course of lecture, philosophy equations from derivation to quasi-linear approximation. Professor Bardos, you are welcome. Please turn on your microphone.
Okay, here it is. You hear me? Do you hear me? Now I admit.
Ils t'entendent pas. Dis-lui que tu les entends pas.
I don't hear you, but you may hear me. Hello? You may hear me. I don't hear you.
Yes, we hear you. Yes. All right.
Allez, full
All right.
screen et tu commences. Non.
Okay.
Non. Voilà.
Okay. Here it is. Okay, you can hear me?
Yes, but please turn on your camera. We don't see you.
You don't see me? Okay.
No, only here.
You see me now?
No, I don't.
The camera is on.
I have the camera on.
But you cannot have camera and sharing of screen. You have to choose.
Yeah.
Can you see him now?
Yeah, here I am. Okay.
Yes.
Now,
Donc ta chaîne ici.
okay. Very good. Do you want me to turn on the full screen? And then you hear me? Okay. Je suis. Okay.
So everything is fine. Please
Can you
welcome.
hear me?
Yes.
Very good. So, if you, whenever I'm ready to start, you say. Okay. Okay. So, I don't know if you hear me. Anyway, I start this talk. Very happy to give a talk at Rouen, to be invited by Alexander. And okay, so let's go. The title was Quantum Mechanics, from Quantum Mechanics to Quasi-Linear Approximation for the Vlasov Equation. Okay. Now, as I wrote on this slide, I want all the way to go, let's say, from particle to something which is called the quasi-linear approximation. And this is a typical way, typical formula for the Vlasov equation. Just an introduction, the Vlasov equation is, among other equations, an equation which involves a kinetic quantity. Kinetic quantity will be a density f of x v t, which describes the number of particles which at the time t and at the point x do have the velocity. And it was introduced by Boltzmann and Lorentz, and more or less that was one of the problem of Hilbert. It was the sixth problem to use this idea, this method of Boltzmann and Maxwell, to derive macroscopic physics from the basic law of at the elementary level. So it's what is in blue at the end of the page is f of x vt. Now, in this program, the Vlasov equation play a special role because they concern plasma physics, and plasma physics is a rarefied media. They are also used to connect quantum mechanics with classical mechanics. And in fact, since any particle field interaction of all the other, there is a weak coupling phenomena, which means that to get the equation, you take one particle and you see how it feels the action of all the other. So that makes it weakly nonlinear. But then, from a mathematical point of view, you have a price to pay because you go very easily, more easily than in other cases, from the particle dynamic to the Vlasov equation because it's reversible. And then from the, it will be most complicated to go from the Vlasov to macroscopic equation, and that will be what I call the quasi-linear approximation, which will be the object of the next talks. Okay, so as I said, I want to organize these 3 talks as follows. The first one will be a presentation of the relation between classical and quantum mechanics and make a formal reduction from n particle to 1 particle, nonlinear, which is the R3 in the quantum case, and the Vlasov in the classical case. Then the second talk, I want to get to the macroscopic equation, and one of the ways is to introduce some randomness, and I try to show you why it is compulsory. On the other hand, going back to classical textbook of physics, this kind of thing were derived for short time just by brute force using some asymptotic expansion. But this gave the ground with the Penrose condition to, in some sense, explore the spectral property of the dynamic and then get, as much as we can, the short-time quasi-linear approximation. So that the plan 1, I go now to Vlasov, 2 stochastic, and 3 expansion. Okay. Okay, just one more word. So if I want to go from particle, that means I start from a number of particles which is very large, 10 to the power 2, 10 to the power 23, and let's say in classical mechanics it's 6 times n, the dimension of the space, 3 for the position, 3 for the degree of freedom, and that's a lot. And if you do quantum mechanics, it will be wave functions, which are defined also on a space of dimension 3 times n. So it's clear that they need to reduce it to a single particle phase space in R6. Now, there are 2 good reasons. First, to answer to the program of Hilbert, to try to derive the law of macroscopic physics from the law of microscopic physics. By the time of Hilbert, that was also a very relevant issue because people were starting to derive, to find out that there were atoms in the matter, and they wanted to be sure that the existence of atoms would be in relation with what we see in real life. Now the point of view has changed because now there are a lot of well-known rarefied media. The most modern ones are related to tokamak, but they are in stellar atmosphere. There are many domains. So it's more in view of application that it is interesting to derive the equation. Okay. So let's to make the thing clear, we can put that in a diagram. On the top, on the left, there is a Schrödinger equation. You let n go into infinity. that will generate the R3 equation. Then that's the upper line with capital N going to infinity. Then you can do two things from this line. You can go down on the left, letting the Planck constant go to 0, where you will get the Liouville equation, which will be a system of n without the same capital N number, coupled equation. Now, on the right, you have already a one equation, which is the R3, and you can also let h bar go to 0, and hopefully in this program, you will get the Vlasov equation, which will be one equation. So, the two linear arrows on the top or on the bottom goes from nonlinear to linear, and the two vertical arrow goes from quantum to classic. Keep this picture in mind and keep that everything being reversible in this business. There is no hierarchy, no entropy which appear. If I would like to go from the left to macroscopic thing, the thing will be more difficult. Okay, move on. So, I want to write, to introduce two types of equation. The Vlasov equation that you know. The Vlasov equation is a Liouville equation, which is just a transport. You will see it several times. It's the action of the bracket of an Hamiltonian, which is on the bottom, c squared plus vf of xt, where v is defined by the action of the potential average on the density of particles. So that's our favorite Vlasov equation. Then you can want to compare to the Schrödinger equation. For the Schrödinger equation, you have n particles, you have n time with h bar, the action of the Laplacian, and you have a potential which is symmetric in the variable xj and xk, symmetric, and it's 1 over n. So in fact, it's what I call the weak coupling that will make the weak coupling, the thing weakly nonlinear, and there you have n squared term, but 1 over n that will give the same order as the Laplacian. With that, you write the Schrödinger equation, and once again, what is in red, it's the idea that you have a mean field constant, which is of the order of 1 over n. So that's our one. Now, to connect this last equation, the Schrödinger, with something to reduce the dimension and get to an R3 or other type of equation, the natural object are the operator density. One of the ways to see that is to take an operator which acts on the variable capital Xn and capital Yn. That will be the kernel. I assume it is self-adjoint. Then I can expand it in the Fourier mode of the Schrödinger equation. This will be the Fourier mode of the Laplacian, of the Schrödinger equation. I assume that it is what is called a trace class, that is trace, that is positive, it's positive, you see that is trace class is equal to 1. That's amount to looking at the fact that lambda k are real, and that the sum of the lambda k are 1. Then in all these things, there will be an hypothesis, which is that all the particles, whether there will be atoms, whether there will be macroscopic particles, are indistinguishable. Which means they are indistinguishable is that if you make a symmetry on the particle, then you get the same thing. If you make a permutation of the particle, this quantity is the same, and the density will be preserved, the kernel, if you make the same permutation on xn and the same permutation on yn. Now you do the same thing for classical density. Classical density will depend the position, they will depend the velocity, they will be assumed to be positive, and if you make a permutation at the same time of xi and the vi and xn and vn, you get the thing is conserved, and also it's a positive density, so the total equal to 1. Okay, that's reasonable. Now, I can write with this density the action of the density matrix, which will Rn capital of n of t. You see that with the definition of this Rn of t, what you can do is just look at Rn of t as the transposed of Rn of 0 under the action of the Hamiltonian group. There is an I missing here, but that maybe you didn't notice. But then the equation for the Rn of t will turn out to be exactly the bracket in the sense of operator of minus h square Laplacian of n plus vi with the operator Rn, while our familiar, and the commutator at this level, while our familiar equation will be the bracket in the sense of classical mechanics between capital Vn square plus, which will be the velocity, plus v of xn with the function f, and I write it explicitly below, just writing what is the bracket. It's Vn dot gradient of xn minus the gradient of xn applied to the potential, applied to the gradient with respect to v of 0. What is really what I wanted to stress here is that with this definition of the operator density, there is a perfect analogy between the quantum equation and the classical equation. So far, so good. Now, what will be the tool to go to from there, just right here, what will be the tool to go from the quantum to the classical? There are several ways to do that. There is a very nice way, which is to introduce the Wigner transform. If you go back, this equation, I call it the Heisenberg von Neumann, because it was already observed by Heisenberg at the level of matrix, and then systematized by von Neumann. Now, as it is here, it has a kernel, the R of variable y, xn, and yn. What I can do at the level of the R3 equation is to replace in this kernel the variable x by x plus 1/2 h bar of y minus x minus h bar of y, there's a y missing on this slide, and take the Fourier transform of this animal. Now, if I make the Fourier transform, when I have a Fourier transform, I can also immediately recover the inverse Fourier transform. So you have rho in terms of w. And so in some sense, rho is what people have discovered as being the Weyl symbol of the density operator R of x and y. And why it is it's a Weyl symbol, and why it is nice because if you look at an equation for the while symbol, which is here, you put it in the equation, and you find out it will be exactly more or less like a Liouville equation. It's a simple formula. It's d over dt of v of h plus xi nabla x of w h, and you take, with the v, you have to take the inverse Fourier transform because you have to apply it to v. You have the difference between these two, the value of v at the point x plus h over 2 minus x minus y. Now it turns out that in the computation there is a 1 over h bar, and you make the Fourier transform inverse. Now, if this quantity, if you just make a Taylor expansion, it's the gradient of x, of v of x, gradient of c, plus an O of h bar, which is small. Bingo, you have obtained the Liouville equation, assuming that this computation will be done in detail. Okay, and in fact, what I point out looking at this thing is that this Wigner transform describes the evolution of the operator, the transmitted operator. Now, what's happened also in our story is that Ormander in the 69 made a big contribution to describe the propagation of the wave front set. And it immediately, G.W. Egorov obtained a theorem to look at the propagation of the operator transmuted by the Schrödinger equation. So, and it's a simple consequence. But he was very happy. He did that also almost in 69. But of course, Ormander worked with potential which are very smooth, which I write which I wrote as being in C infinity, which is not the case of a potential involving the action of the inverse of the Laplacian, or even with a small regularity, like for the R3 Poisson equation, or even for a Lipschitz potential. So this Egorov point of view was inspiring, but then you need more sophisticated thing if you want to use that for a Vlasov equation. Okay, now that's the root for the vertical trace. Root for the horizontal trace is also something which is quite classical. What you do, you have a function which depends on many variables. You will just reduce it by reducing the number of variables from capital N to small n by integrating over all the variables which range between small n and capital N. And you obtain for the density the equation which is below, which is the equation which depends on capital N, small n, the bracket of the Laplacian as the degree small n, because you can integrate through, and also 1 over n, the action of the potential, and you integrate 2. Now, if you want to do the same thing for the other variable, the variable that are between small n and capital N, you get a more complicated term. But since you assume that you have invariance under permutation, all the complicated terms, they are all the same, but they are capital N minus small n. So you see them, they are here, and what is striking is that to go from capital N to small n, you need this equation, and thanks to the fact that it is invariant by permutation, all the terms are the same, and you just act with the n plus 1. So to know rho n, you will need to know rho n plus 1. To know rho 1, you need to know rho 2. To know rho 2, you need to know rho 3. It is what is called an hierarchy. And if you let n go to infinity, this remains, this goes to 0, and this goes to 1, and it's the equation which is below. Okay, very good. And what is striking is that if you want to do the same machinery for the classical system of n particle and the Vlasov equation and the Liouville equation, you will do the same thing and you will arrive to an infinite set of equations. The algebra is the same, it is just written down. You start from this system and you end up with simple equation, Vlasov equation, Liouville equation, except that instead of the n here, you have an n plus 1 here. Instead of the n, you have an n plus 1. Okay, that's the first was the Schrödinger hierarchy. This will be the Liouville or Vlasov hierarchy. Okay, now all this hierarchy, they are called BGKY hierarchy. The name is from Bogolubov, Born, Green, Kirschwood, and Yvon. Okay, as a talk from people from Paris, I will have to make 2 comments about Yvon. Yvon derived this equation in 1936, and it was rediscovered 11 years independently by the other author. What is striking is that it appears in different type of way in many other problems of statistical physics, and it will be present in my other talks. And it's what is striking, it's really the similarity between the hierarchy for Schrödinger, the hierarchy for the classical dynamic, and there is a very good important observation is whenever this hierarchy is this density operator is factorized, then to be a solution of the infinite hierarchy, it's enough that the first row x1, y be solution of the R3 equation, and for the Vlasov equation is the same thing. Instead of the hierarchy, it's enough to have solution of the small f be solution of the Vlasov equation. So here once again I want to show you this thing. Here you have the R3 equation, so that I wrote for assuming that it's a product. And here I wrote the Schrödinger equation. You can, if this row is a phi x phi y, whenever psi is solution of this equation, it will be solution of the hierarchy. And you have the same property for the Vlasov equation. Okay, so far so good. Okay, just comment about the proof. I think really it's a period of the time I have been start to work in mathematics. I think the first proof of the derivation of all these things, in particular the R3, was in a paper of Herbert Spohn in the Review of Modern Physics in 1980. It's systematic, it contains everything. There are a lot of detail which are more or less missing, but there is the essential. The essential idea are really in Spohn paper. Then there is a more modern, what we did with Goltz, François Goltz and Norbert Moser. We wrote a kind of systematic, maybe in the style of Bourbaki, description of the way to go from the Heisenberg von Neumann, the equation for the n particle, to the R3 equation, but we use just the proof was valid using the trace norm on the operator and using that the potential be bounded, even more bounded than the potential be Lipschitz. In fact, I wrote bounded, but I really need Lipschitz. When it's Lipschitz, it works very well. And for that, You need to look at the convergence of the operator. For that, you need a trace, use a trace norm. And when you end with the hierarchy, then for the uniqueness of the solution, you use the abstract version of the Cauchy-Kovalevsky theorem. And all that, as I said, it's required the potential to be Lipschitz, which means bounded derivative, which has nothing to do with the 1 over x minus y, who is the singularity of the inverse of the Laplacian. Okay, so I move slowly down now to move the first arrow, to go from the Schrödinger, which is to go. I should go back. I hope you have the Schrödinger equation in mind with n particle, and then I want to repeat that to go from the Schrödinger to the R3 equation, the program was extended, and it was extended in a paper of Erdős-Yau in 2009. The idea is, if you want to balance the singularity of the potential, you use an estimate which is preserved by the dynamic of the n-particle Schrödinger, the trace class operator, which is that if you take minus h squared over 2 the Laplacian, you tense it on all the variables. You look at rho of n reduced at the small n in the hierarchy. This quantity is bounded by its value at the time 0. So if you fix h, this has introduced enough regularity to make the problem work. Okay. Now, just to note, recently, or in 2009, there was a proof which is quite clever, which directly get an estimation of the difference between what the operator in capital N and what you do between the factorization of n times the 1xi. And it's a proof which is quite clever, quite direct, which is given by Pickle, and it's in Letter of Math Physics 2000N. So, as I said above, so that takes care of the two horizontal lines. Horizontal line, but as I said above, to go then from the Vlasov or the R3 equation, if V is in infinity, it's easy if you by the Egorov theorem. Now for Coulomb potential, it's really more serious. In fact, it's interesting. It was in the paper of Lyons and Paul in 1993. They have two types of things. First, they have to show, they want to show that the limit, because the limit at with h bar going to 0, it will be a density solution of the Vlasov, so it has to be positive. And if you make a Wigner transform, you introduce some oscillation. Now, there was one thing interesting which was observed, is that if you modify this Yushimi transform by introduced by Schutz, applying the action of the Laplacian here, of the heat equation, then in the x and xc variable, you introduce another animal, but this one is nice because it's positive, but its limit will be the same as the other. So you buy that the limit of the Wigner transform is a function which is positive. And second, I mentioned already the trace estimate, that this quantity, the trace norm of this animal, with the density here, was bounded by its value at time 0. But there is an h bar. But if you do that, you have a tool which will all to improve the thing if you can keep this property when h bar goes to 0. Now, if you want to keep this property, you have to take initial data, which depends on h bar, which goes to a nice density, when h bar goes to 0. Well, this is not so easy because if you want, with the h bar de Laplacian, if you take just a standard WKB bound state, it doesn't work. What was found out, and it's very interesting, that if you take mixed state, a combination of eigenvalue of the Laplacian, an infinite one, and the sum is equal to 1, then everything was okay. And just to quote once more Jean-Pierre Yvon, Jacques Yvon, it was published already in its observation at the level of physics with no proof, like in Lyon's Paul, very the physics type proof. It was published in 1946 in Compte rendu de l'Académie française, and it was based on note that he wrote when he was in a concentration camp detained during the war. Yvon was a very strong guy. Okay, now I want to quote two other point of view which are to be compared. One is one to be compared and then another extension. One is the idea to keep in mind is the Klimantovich solution. You see, instead of looking at a system of n equation, you just look at one equation in d time n dimension. So you have capital N equation, and you move the point to a solution that will be just point with the xi equal vi. The derivative with respect to time is vi, and the derivative of vi is minus 1 over n xi, the sum of xi minus xg. And this is an ordinary nice equation, and with this ordinary equation, you look at the evolution of a distribution. And this distribution is called the empirical measure. You take 1 over n, you take the sum of delta of x minus xi depends on time, delta of vi minus vj. So it's a product of a delta on x times a delta on y. It works very nicely. It's a density measure on Rx at the point Rx of the point V. So you have n particle, 1 over n, but they all live in the same space, Rnx of Rnt. Now you find out that it is exactly a solution of the Vlasov, of the standard Vlasov equation, provide you check this relation in the sense of distribution. Except that you also, to make sense to that, you better to take a potential, which in this case will have a gradient which is in L infinity. So, and this equation is called the Klimantovich equation with respect to Vlasov. Now, you have to find, and it satisfies this conservation of energy. Now, one line more, you have to try to find the convergence in the sense of measure. There was a first paper by Neuzert and Wick, which are generalized by Braun and Epp, but in this review of all the different approach, I think I want to quote the Dobrushin argument, which is really slick. What Dobrushin said is that since this empirical measure are measure, the tool to use is the Wasserstein distance between the mu and the mu, and you define the Wasserstein distance by taking, which is also called the Monch-Kantorowicz distance. You take the this x minus y, dx dy, where mu and u are measures which project on the space dx dy, but for the x you integrate with respect to y, for the y we integrate with respect to x, and this you get an equation. And what Doboshin found was that you have for this equation a very nice Liouville type, Grondwald type estimate, because it's classical, you can just integrate several times, and you have a Grondwald estimate, not for norm, but for this Monch-Kantorowicz distance. And that gives by you the convergence and the fact that directly you have another way to see the limit of Vlasov as a limit of system of n particles. That's it. And then just to finish, I want to say that this thing has been done at the level of classical dynamic, going to n particle classical to go to the classical Vlasov. One is there was an idea, a systematic program of expanding this idea not only to classical mechanics but to quantum mechanics. The way to do that, and I won't go in the detail, is to introduce the quantum analogous of the empirical measure. You control the quantum analogous of the empirical measure that define the distance in the level of quantum operator, and with that you can construct all the same thing as in Doboshin, and the way to do that you obtain things which are invariant in independent of h bar. So if I go back to the first slide, which I will, to conclude, I will go there. So this is construct even for Coulomb potential, even more singular. And this arrow is also concerned with a down here by the work of Paul. Directly here is just from Schrödinger to Liouville, is just the Wigner transform, just the work of the extension of Egorov to the case of potential which is singular. This arrow red is the recent paper of Goltz, Muo, and the other people of this group, and it gives a limit directly when n goes to infinity and h goes to 0, but the price to pay was that they used the Doboshin, the extension of Doboshin method to a quantum version of the empirical measure. So here, as in the classical case of Doboshin, they were not able to, or up to now, they are not able to consider other things than potential that will be Lipschitz. I thank you very much. I think my time is done.
Thank you very much, Professor Bardos, for your lecture. We have some questions for you. The first question is, do the results and equations before page 13 relate to the whole space or domain with the boundary?
Okay. And this type of problem, people, and here they have not attacked the systematically. Okay, I should, can I see, can I move to, okay. Okay. Okay, yeah. Yep. Yeah. Oh, I see people. Okay. Very good. Do you see me? Okay, you see me at least.
Yeah, yeah.
Okay. So basically, what I talk about now was for problem with no boundary. Even less, even more some of them are even worked in domains which are just identified with periodic function, which means really both bounded, depend on the different case, both bounded and with no boundary, like a periodic function. It's extended, it can be extended very reasonably if the space is a bounded domain, and on the boundary you assume specular reflection. But I think there is no, up to now, a systematic study of what is the influence on the boundary on this type of program. Or except when the boundary is really flat, because people look at what is the relation between the atom or the molecule which are on the air and the atom of the molecule on the boundary. So there are certain.
Okay, thank you very much. And the next question is, looking ahead, what would be the main challenge in the investigation of the Vlasov equations now and in the near future?
Say it again.
What would be the main challenge in the investigation of the Vlasov equations now and in the near future?
What will be the domain change, I think? I think it's not done, but that's the thing to do, sure. If I got it. No, okay, you have. Okay, what I wrote, discussed here was a complete picture for, let's say, very mathematical domain. I apologize for that. Either no boundary, either with, and I really think that's, let's say, the thing to do maybe will be first to look at the wave equation, because it's an Hamiltonian equation in a domain which change. And there are already some work where you look at the wave equation in a domain, for let's say the standard wave equation or Schrödinger equation, in a domain with bounding with a boundary which moves. And where it moves, let's say, it has to stay in the wave cone in some sense. And then I don't have a reference in my head, but I think that do exist. I can send that if someone asks me references.
Okay, thank you, Professor Bardos. And the last question for you. Can you describe more precisely how the Boltzmann equation is related to Vlasov equation?
Okay, I can tell you it's really the opposite way in what they share in common. Boltzmann and Vlasov are both constructed from a hierarchy. That's the common point. Now I tell you what is the difference. The difference is that the Vlasov, or the one I talked today, was based on a mean field hypothesis, which is you take one particle, classic or quantum, and it is the average of its fields, the average of all the other, which means there is a 1 over n over in front of the interacting potential. That, and as a consequence of mathematics, you go from a reversible problem to a reversible problem. And if you want to go to macroscopic equation, which will not be reversible, you have to work more hard, which is the thing I want to talk about in my other lecture. So that's for Vlasov. Now, compare with Boltzmann, it's the opposite. The original idea of Boltzmann was to look at the interaction of two molecules, once again the other by a shock. A shock is very strong. If you write the hierarchy, there is no 1 over n. It's a model of the very fully non-linear problem, which means deriving the Boltzmann equation from the Vlasov equation, from the classical dynamic. It's an old problem. It goes back to Boltzmann himself. But as far as proof, the first one was done only by Lanford in the 50s, long time before Boltzmann derived the equation. And the proof is very hard. He had to follow how many times one particle will hit any of the other. And the result that he got, which was really, is that he validated this equation, the derivation, only for a short time. So that's very difficult. And there was some improvement by Gallagher, Saint-Raymond, Bodino, which are quite clever, and maybe we could talk about that later on. But basically, it's the hardest part of the problem. Then, when you have done that, irreversibility has appeared, entropy has decreased, and at this level, going from Boltzmann to Navier-Stokes, maybe I should not say this is easy because it has all the people in the French group have been working on that for 40 years, but it's completely solved. It's completely solved because you already start from Boltzmann, where you have already an entropy, and you go to the macroscopic. In all these things, the difficult thing is the place where the entropy should appear from a dynamic at the elementary level, which is fully reversible. And there are several places where this is very well. I strive to prepare, maybe independently of the slide of my lecture, I may try to prepare some reference, but this what you could keep in mind. Some problem, it's difficult when you go from particle to the first step, because you lose entropy, and then the second step is easier. If you don't lose entropy, it's reasonably easy. It's a survey talk, as I did, but then going to the next step is more complicated. Did I answer?
Thank you very much. I think it's clear now. And again, thank you for your lecture, for your answering questions. We are looking forward for your next lecture tomorrow.
Okay, thanks a lot.
Dear listeners,
I to fix the machine now.
Okay, dear listeners, we have a rest about 8 minutes before the next lecture.
Okay, thank you. Bon.
Вон ты уже вылез. Внизу, в левом углу, в правом углу ты. Видишь правый?
Это я включил.
Ну все, давай. Вон ты смотришь. Вон.
Нет,
вот,
я вижу.
вот.
Я вижу. Вот.
Закрывать тебе. И ты нервничаешь.
Я не пойму, как они меня будут видеть.
Dear listeners, let's continue our workshop, and our next lecturer is Professor Vyacheslav Grines from High School of Economics with the course on interrelation of regular and chaotic dynamics with topology of an ambient manifold. Please ask your questions. Professor Grines, we don't... now we hear you.
You see my lecture or not? My presentation. Hello?
No, we don't see it now.
What I must do?
Share your screen, please.
Share my screen, yes. I open my change content, yes? But, okay. Okay. Now, you see?
Yes, we see. Okay.
Thank you very much. So I can start. So I am very glad that I got invitation to this beautiful conference, and I am glad to start my mini course of my lectures on the relation of regular and chaotic dynamics with topology of an ambient manifolds. So first lecture today. So what is mean Morse-Smale system? Morse-Smale vector fields were introduced by Stephen Smale in the paper Morse Inequality for Dynamic System in this journal a smooth vector field X on smooth and manifold cement with following properties. X has a finite number of hyperbolic singular points. X has a finite number of hyperbolic closed orbits. Stable and unstable manifolds of where these objects have transversal intersection with each other. Okay. I would like to give some citation from paper by Smale. We remark that systems satisfying condition 1-3 may be very important because of the following possibilities. A, it seems at least plausible that systems satisfying 1-3 form an open dense set in the space with C1 topology of all vector fields on a manifold N. B, it seems likely that conditions 1-3 are necessary and sufficient for X to be structurally stable in the sense of Andronov-Pantriagin. A, B have been provided for the case Mn is a two-disk. What I would like to emphasize, that both hypotheses, A, B, is not, it's occurred that is not true for manifolds whose dimension more than 2. So this hypothesis was mistake by Smale, but he saw these mistakes himself and class of such systems. And all people know that Smale is one of the person with an author who opened hyperbolic revolution in dynamical system. So class system with condition AB occurred very important indeed, but these systems are not dense in all space of all systems, and it is not necessary condition for structural stability because Smale very soon constructed example of flows which is structurally stable but has countable set periodic orbits. However, these systems was not called by more Smale. Maybe it will be better to call them by Andronov and Pantriagin, who introduced the concept of structural stability, but it's not structural stability concept. First concept was called rough system, but this, according to an author, these concepts are equivalent. These systems are important because they are mathematician models for very important process in natural. Okay, so continue. In my talk, I will deal with discrete dynamic system, and I will call them by more Smale diffeomorphism. Definition. Diffeomorphism of Mn to Mn is a more Smale diffeomorphism if its non-wandering set consists of finite number of hyperbolic periodic points. Stable and unstable manifolds of different points from omega f have transversal intersection. I try to recall all concepts that I use in my lecture. So definition, one says that two smooth submanifolds x1, x2 on a manifold Mn have transversal intersection if this condition holds for any point x which belongs to intersection x1, intersection x2. Okay, next. Definition. A point x is called non-wandering points for a diffeomorphism f if for any neighborhoods x of the point x where is number n such that iteration with neighborhoods intersects origin neighborhoods. In opposite case, the point is called wandering point. It's clear that fixed point and periodic points are non-wandering points. And in my talk, I will use only periodic points. So my non-wandering set will be union of periodic points, periodic and fixed points. I recall also a periodic point P of period M of the diffeomorphism F is called hyperbolic if a differential considered as a linear map of tangent space has no Eigen values equal modulo 1. Only modulo less 1 and modulo more 1. Okay. Very important. Also, we already use the concept stable and unstable manifolds. So I recall stable and unstable manifolds of hyperbolic periodic points, where hyperbolic periodic points P of period M were so-called stable manifolds, which defined this formula. It's set of X which iteration tends to point P when n go to infinity, and unstable manifolds with iteration for negative discrete time tends to point P. So we connect with any hyperbolic periodic points two invariant manifolds, stable manifolds and unstable manifolds. These manifolds plays very important role in dynamics of diffeomorphism on manifolds. It's understood small role of this manifold. Okay. Very important concept is concept of Morse index and types of periodic points. The number eigenvalue or Jacob matrix whose module is more than 1 coincides with the dimension of unstable manifolds, dim WP, and is called the Morse index of a hyperbolic point. Okay. Then the dimension of stable manifolds is calculated by the formula dimension WP is equal n minus g. So we have three types of hyperbolic points: sink, saddle, and source. In dimension 3, in this picture, we see sink, index Morse is equal 0, saddle with index Morse 2, saddle with index Morse 1, and source has a fixed point or periodic point has Morse index 3. So it's very important to imagine the picture. It's phase portrait of trajectory. It's discrete orbits, which in the case of sink, they tends to sink. If we have saddle index 2, we have two-dimensional invariant manifolds, surface. For all points on this surface, leave any neighborhoods of saddle, and one-dimensional manifolds, if we take point on one-dimensional, it will be tends to saddle. Similar for saddle with index Morse g равным is equal 1, and source, all points leave neighborhoods, any neighborhoods of source, okay, which all iteration leaves any neighborhood, okay. So very important role in a dynamical system has intersection of stable and unstable manifolds of different saddle periodic points. For simplicity, in the future we can speak only about fixed point if you want. So you can look at the picture and you see fixed point. For example, if we consider left picture, what we see? We see saddle sigma 1, we see saddle sigma 2, and stable and unstable manifolds of these saddles have intersection. And this intersection if dimension of stable and unstable manifolds are equal to, I would like to emphasize that now we consider only three-dimensional case. This curve called heteroclinic curve. On the right picture, we also see intersection of invariant manifolds of two Sandel, sigma 1, sigma 2, and the intersection is compact heteroclinic curves. In first case, it's possible to prove that number of connected components non-compact is finite. It's a beautiful fact. But if we consider compact heteroclinic curves, this number must be infinite set. So such curves play important role in dynamics because it's necessary to explain, and I have no time in my lecture, but it's mathematical models for separators in magnetic fields. So it's very important object. And existence of heteroclinic curves very important for describing magnetic fields, because it means that we have some separators, and it's very important for physicists. Okay? Continue. Let sigma 1, sigma 2 different periodic saddle points such that intersector is not empty, but dimension one has dimension 1 and another 2. So dimension W sigma 1 plus dimension WS sigma 2 is equal 3. Then any point in this case is called heteroclinic points. Heteroclinic points and existence of the heteroclinic orbits also is very important for dynamics, because it's in some sense corresponds to existence of solitons, and so it's also important object. And the existence of this object play important role in describing of dynamics of dynamical systems. Okay. So also for me in my lecture, very important to consider the case that unstable or stable manifolds of saddle of given saddle have no heteroclinic intersection. So it's very important what happened with asymptotic behavior such invariant manifolds. Let F M3 be M3 be more small diffuse and sigma as saddle point for which unstable, for you can think about stable as the similar. I for simplicity consider in this only in this moment I say about unstable manifolds is one-dimensional or two-dimensional. Connected components of a set WP minus P are called separatrices of a point P. It follows from small that if a separatrice L, look at picture, L or lambda does not contain heteroclinic intersection, then closure of this object is homomorphic or segment, you see segment, green segment in one-dimensional case, or sphere S2, because we consider these manifolds, these separatrices, and the closure of this separatrice will be sinc omega. All point which belongs orbit of this, each points on this invariant manifolds tends, and all iteration tends to omega 1, and we get sphere, two-dimensional sphere, which consists of this separatrice and 2 points, sigma and some sinc omega. Okay, so it's one case for dimensional and two-dimensional. Similarly, if we consider stable manifolds, we have sphere in this case, or segment of this case, which consists of stable manifolds and some points, which is source. Okay, so I would like to emphasize that very important that you imagine what geometric construction which I explained, because only in this case you can understand how I get my result. Okay, so a few words about topology. A manifold M3 is called connected sum of manifolds M1 free and M2 free, and we write M3 is equal M1 ds M2. If M3 is obtained by choosing free balls, we take free ball, take free balls here, delete them, and glue in boundaries, which homomorphism reverses the natural orientation of the boundaries. So if we delete two balls from manifolds and glue in boundaries, we get new manifolds, which is called connected sum. Okay, so I recall that manifold M3 is called irreducible if any two-dimensional sphere timely embedded in M3 bounds on three-dimensional disk. Our space, three-dimensional space, it's three-dimensional manifolds and such that is irreducible clearly. The manifold M3 is set simple if M3 is closed and if M3 is irreducible or homomorphic to S2 times S1. Look at the picture. What is mean S2 times S1? Let us consider annals between two spheres, first sphere and more sphere, which has the same center. And we consider annals between them. And it's not closed manifolds. These manifolds, annals have two boundaries, these boundaries and another boundaries. But if we glue in the point 1 to this point, which lie on common radius, okay, then we get manifolds which we call S2 times S1. These manifolds is called S2 times S1. In two-dimensional cases, we glue in, if we have two-dimensional angles and we glue in these points, we get torus. But in three-dimensional case, we don't get torus, we get manifolds which is 2 times S1. So we have very, very important and beautiful theorem, Nether-Milner decomposition theorem. Any orientable closed manifold M3, what does mean closed manifold M3? It's manifold M3 without boundary, can be decomposed into the connected sum of simple manifolds, and the decomposition is unique. So any three-dimensional manifolds, closed manifolds, is connected sum of S2 times S1 and irreducible manifolds. What these irreducible manifolds, we don't know, but we would very good imagine what is manifolds S2 times S1. The main result of my lecture that very beautiful, important classes of system, Morse-Smith system, regular dynamics system, ambient manifolds may be only connected sum S2 times S1. So I try to formulate this theorem. Topology of ambient manifold admitting Morse-Smith diffeomorphism without heteroclinic curves. Suppose that we have Morse-Smith diffeomorphism and saddle invariant manifolds can have intersection, but only heteroclinic points. We have no heteroclinic curves. In this case, manifold M3 is connecting sum S2 times S1. So we know the topology of any such manifolds. And the number of members of this connected sum is equal number or k minus L plus 2 divided by 2 copies of S2 times S1. More exactly, when M3 is sphere, if k is equal L minus 2, or M3 is connected some k minus L plus 2 divided by 2 copies of S2 times S1, where K and L very simple numbers. K is the number of all saddle periodic points, and L is the number of all sinks and sources of diffeomorphism F. So, what beautiful theorem we have. If we consider diffeomorphism F3 to F3, more small diffeomorphism, then we nothing know about topology of manifolds M3, but we know that these diffeomorphisms have no heteroclinic curves. If you remember, compact heteroclinic curves, non-compact heteroclinics. So it means that two-dimensional separatrices have no intersection for saddles. But two-dimensional, one-dimensional can have intersection. In this case, we calculate number of saddles, k, calculate number sinks and source, and consider fraction k minus L plus 2 divided by 2. And we claim that our manifolds is connected sum of S2 times S1. This theorem was proved by me, Bonatti, Medvedev, and Pecou. So it's collaboration with me and Medvedev with French mathematics. And as a result, in my lecture, I consider only first part of this theorem. Second part, that if we consider number k, L, such that k minus L plus 2 divided by 2 is not equal to 0, is 0 or positive, when there exists some more small differ without heteroclinic curves, with which is manifolds is connected sum S2 times S1. So it's possible to construct representative of any system of such view. Okay, but today I have time to give sketch of proof of this theorem. I would like to explain how a pair S2 times S1, how a pair connected sum. I would like to explain that manifold in this case has very simple structure, because S2 times S1 is clear what's, and we consider connected sum of this object, and we get manifolds, and only with manifolds admits such topology without heteroclinic, one-dimensional heteroclinic curves. Okay, so let us start to prove. So the theorem above, it's very important, because it's not interested only what manifolds we get. It's very important for application, because the theorem above is sufficient condition of existence of heteroclinic curve for given more small diffeomorphism. For example, if omega f of diffeomorphism f S3 to S3 consists of two saddles, one sink and one source. Okay, we don't know nothing more about this system. When we claim that wandering set of such diffeomorphism contains a heteroclinic curve. So we understand that there are many places in S3, but we have only 2 points, sink, source, and 2 saddles. And I claim that stable and unstable manifolds, two-dimensional, must have intersection. Moreover, in this case, there is at least one non-compact heteroclinic curve. For physicists, means that such model has at least one separator in magnetic fields. And we published some paper in Physica D that we give the sufficient condition of separators in magnetic fields using by this theorem. It was published in a few years ago. If ambient manifolds of Morse-Smale diffeo F is not homeomorphic to connected sum of copies of S2 times S1, for example, if ambient manifolds is the torus, it means that phase space is free torus. It means that arguments of our dynamical system is cyclic on free coordinates. Then omega F contains at least one heteroclinic curve. So if we have system on torus and we claim that if omega F contains at least one heteroclinic curve, so it's very beautiful result because we nothing more know about dynamical system. Only that phase space is free torus. And if we have on free torus Morse-Smale dynamical system, it means that stable and unstable manifolds must, two-dimensional, must have intersection. So topology sometimes very beautiful, help to understand dynamic, okay? So on existence of two, so now I start some sketch of proof. Lemma. Let Wandering set of Morse-Smale diffeo does not contain heteroclinic curve. Then there is a saddle periodic point such that AVWP or WSP has dimension 2 and does not contain heteroclinic points. In this picture, you can understand proof of this lemma. So I claim that these manifolds have no, so we can find such saddle that two-dimensional stable or unstable has no intersection, heteroclinic points. But for condition we have no heteroclinic curve, so we have no heteroclinic intersection, and close of this separatrice be sphere. If we suppose the contrary, we come to the contradiction in finiteness of the non-Wandering set omega F. Look at this picture. Let's consider this saddle. And suppose that this separatrice intersects these stable manifolds of the same saddle. It's not possible because Poincaré already knew that in this case our system will have infinite number of periodic points. So it's not possible. So these separators go to another two-dimensional separatrice intersect. And if this separatrice of this new saddle go to this, so we get cycle on two saddles. Also, it's possible to prove that non-Wandering set not will be finite. So we will consider next saddles. And after that, after that I understand that because saddles finite number, so we find separatrice which not go here. It means that we get such picture. This separatrice is two-dimensional, have no intersection, and asymptotic behavior is some source. And we get sphere, So, it's some repeller with invariant manifolds with this alpha is invariant set which is repeller because all point leave some neighborhoods of these manifolds. So it means, suppose for definiteness that there is point P such that WSP have dimension 2 and does not contain heteroclinic points. As by assumption, WSP does not contain heteroclinic curves when by Smale there is a source such that this union is homeomorphic to the sphere. So after that, new lemma. There is an open domain K such that sigma, our two-dimensional sphere, belongs to annals between two k as 2 times, with k is annals, and k is diffeomorphic as 2 times interval, and where is m more than equals 0, such that more 0, such that under negative iteration of these annals will be belongs to annals. So it's repeller. It means that for negative powers of diffeomorphism is attractor. Okay. So what I would like to very quickly to emphasize, it's from first point of view, it seems very simple fact. In some sense, it's very deep lemma, because with manifolds, with sphere, not it's very smooth sphere where expect alpha, but in this point alpha, this sphere may be not so good embedded. So while embedded separatrix, let's notice that closure L of separatrix everywhere is smooth except maybe at omega. So a topological embedded L clause may be complicated at neighborhood of the sink. According to Artin Fox, L called is time if there is a homeomorphism which maps this widely embedded curve to its timely embedded if our curve is homeomorphic to good ray. But it's not homeomorphic, it's not timely embedded. And Artin Fox constructed examples of wiretap in this year, but they did not think about dynamic. But rather recently, Pixton considered diffeomorphism with more small diffeomorphism before, only for fixed points, omega 1, omega 2, sigma 1, sigma and alpha, such that two-dimensional separatrices are widely embedded. And it means that such systems, countable set, non-conjugated systems, very simple dynamics. And it was proved by me and Bonatti in not so recent time. Okay, and I would like to emphasize, if we can see the sphere which have 2 points of wideness, this sphere have no good neighborhoods, which claims our lemma, Lemma claims that if we consider such sphere with only maybe bad point alpha, this sphere bad, but we have good annals with good boundaries, with very good boundaries. It's very important place in our sketch of proof. I try to stop at minutes and think about it. So we have sphere, which is our separatrice, closure by alpha. We understand that it is a sphere, but this sphere is not so good in alpha. It may be widely embedded. However, we can put this sphere in the good annals with very good boundaries. It's key place for our construction. Okay. Okay. Cut and glue operation, find it of copy as 2 times S1. As I already said to you, but very important to explain you how it appear as 2 times S1. Unfortunately, I can draw picture in three-dimensional space because there are no compact manifolds which can embed it in free space. But so it's in some sense 2-dimensional surfaces, but I think about free manifolds. But it's possible to understand how appear as 2 times S1. For a 2-dimensional case, appear as 2 times S1 times S1. So appear torus instead as 2 times S1. Look at a picture very carefully. The boundary M3 minus K consists of 2 connected components, diffeomorphic to the sphere S2. that is glued to these connected components the boundaries of smooth free balls and denoted by M tilde free new manifolds. Okay, so we consider, if you remember, we prove our lemma, we consider sphere and consider neighborhoods, annals K, and we delete this K from manifolds, and it's clear we get two spheres and gluing balls to these boundaries. So there are two possibilities. M tilde free is connected, and in this case M free is homomorphic M tilde free and S2 times S1. Appear S2 times S1. If you look at picture left, you delete green annals, and it's clear that if it's the surface of genus free, two-dimensional case, and we get surface genus 2, and it's clear that it's necessary to add torus for this form connected sum with torus, and we come back our origin manifolds. Okay, so it's possible exactly to prove it's some topological result. It's necessary to special to prove, but it's clear geometrically. If M3 is connected, and in this case M3 is homomorphic to some M tilde free connected sum S2 times S1. And next case, M tilde free consists of two connected components, and in this case M3 homomorphic to M1 free connected sum M2 free. Okay. Without loss of generality, we can suppose that omega F consists of fixed point. Yes. In both cases above, one can construct a more small differ F tilde M3 to M3, whose non-wandering set contains K minus 1 saddles, because we delete one saddles, fixed points, and L plus sinks and souls, because we glue in balls and construct new more small, which we deleted saddle, but add sink or source. After continuing this process, we we get new manifolds M tilde, and then cutting manifolds again, and so on, so on. What we get after that? Let G be the number, the kinds of saddles. Let G, denoted by G, the number of saddles for which closure of two-dimensional unstable or stable manifolds does not cut appropriate manifolds of two connected components. It's possible to say that this saddle give us S2 times S1. In this case, after cutting of anomalous neighborhoods and gluing balls, we find copy S2 times S1 in the composition of manifolds M3. Then K minus G, K is the number of false saddles, if you remember, is the number of saddles whose closure of two-dimensional unstable or stable manifolds cuts appropriate manifolds on two connected components. Okay. After all cuts, we get the manifolds which admits more small diffeomorphism, whose non-wandering set consists only sink and source, because we delete all saddles. But if we have manifolds which has only one sinks and one source and nothing more, it's possible to prove this manifolds is sphere. It's very easy to understand this fact, because if we have sink, we have ball which surround this sink, and all points tends to sink. And we also have alpha, it's also a ball. So our manifolds is two balls gluing by boundary. It's well known that we get S3, sphere S3. Here is very important for that we, when we cut it, our manifolds with boundaries will be good manifolds. So I explain that it's not, we must be timely embedded. Consequently, this manifold is the union k minus g plus 1 copies of free spheres. As each sphere contains exactly one seed and one source, we get equality k minus g plus 1 is equal to plus L divided by 2. K number of saddles, L number sink on source, so number of spheres will be this number. It follows this equation that G is equal K minus L plus 2 divided by 2. And consequently, M3 is connected sum of K minus L plus 2 divided by 2 copies of S2 times S1. That is, the theorem is proved. So, in fact, I prove my result. Next lecture will be devoted to the case that we admit heteroclinic curves, but we don't admit heteroclinic points. And then we get Hegar decomposition of our manifolds. So we again get very close interrelation between dynamics and topology of manifolds. But it will be a next lecture. So thank you. And I would like to say that all facts and the proof of this theorem, it's possible to look at our book. And in my abstract, I gave references to our proof, was written by my former aspirant Olga Pachinko and my colleagues Timur Medvedev. Okay, and it's published in Springer. Okay, so thank you very much for your attention.
Thank you so much, Professor Greenes. It was very interesting. Now we don't have any questions, but I hope they will appear maybe on our discussion today in the evening. And we are looking for your next lecture tomorrow.
Okay,
dear listeners, thank you so much.
Thank you.
Dear listeners, in 10 minutes we'll continue our workshop. Now we have a short break.
Dear listeners, we are going to start the last lecture in today's program, the mini course called Reaction Diffusion Equations in Biology and Medicine. Will be given by Professor Tali Wolpert, Senior Researcher in CNRS, National Center for Scientific Research, France and Lyon University. He is also collaborating with Rudean University. Please don't hesitate to ask any questions. Now, Professor Wolpert, please start.
Good evening. Thank you for this presentation. And I would like also to thank the organizers for the invitation. It's a very interesting workshop. So the title of my lecture is Reaction Diffusion Equations in Biology and Medicine. And it will be 3 lectures. In the first lecture, I will briefly recall the applications of reaction diffusion equations, and then we will discuss some questions about existence of solutions, namely about existence of waveform pulses. The second lecture will be devoted to stability of solutions, and in the last lecture we'll discuss in more detail some applications of these mathematical results in population dynamics and in mathematical immunology. So first of all, what is the reaction diffusion equation? It is shown here. U of X and T here can describe temperature distribution or concentration distribution depending on applications. It can be density of some population and so on. So the first term on the right-hand side of this equation, the second derivative, it can be usual mass diffusion or heat diffusion. It can be also random motion of the individuals in some population. And the second term in this equation, the reaction term, it describes heat or mass production or reproduction rate for some population. It can be one equation as shown here, or it can be also systems of equations. So the theory of reaction diffusion equations begins about already 1 century ago due to several applications, in particular to heat explosion, in the time developed by Semyonov and Frank Kamenetsky. The second important application was related to population dynamics and combustion. So well-known works by Fisher and KPP. KPP means Kolmogorov, Petrovsky, and Peskunov. And in combustion theory, this another interesting and important application appeared related to parton formation. It was the work by Alan Turing in 1952. So I will briefly recall these works and these applications. And the first one is the theory of heat explosion. In particular, here you see on the slide this equation here for the temperature distribution suggested by Frank Minsky. This is called Frank Minsky theory of heat explosion. It was developed at the time to describe gas explosion in coal mines, but of course this question remains also important nowadays. You can see on this figure, picture on the right, this huge and terrible explosion happened several weeks before in Beirut. And the theory of heat explosion, this equation for the temperature distribution with this heat diffusion described by the Laplacian and this reaction term describing heat production. So this equation can have stationary solutions, and if the stationary solutions exist, then the temperature remains bounded. If the stationary solutions do not exist, then the temperature goes to infinity, and this case corresponds to heat explosion. So this is a good example which shows how classical mathematical equations related to the existence and stability of solutions describe real world and important physical problems. Another interesting and important applications of reaction diffusion equations is related to wave propagation, and then we need to cite these two famous works by Kolmogorov, Petrovsky, Piskunov, and Fisher appeared approximately at the same time, 1937-38. They considered the same equation shown here with the function f shown here, this figure, and for the first time for these parabolic equations, semilinear parabolic equations, they considered the solution of this type shown here, u of x and t equal wx minus ct. These are so-called reaction diffusion waves, or mathematically speaking, traveling wave solutions. The constant c is the wave speed. So these are solutions which are shown here in this figure at the bottom. It's a solution propagating with a constant speed and with a constant profile. So I repeat that these are reaction diffusion waves, and it appears that reaction diffusion waves describe many different applications in many different fields, and I will show you here several examples. Probably most well known. One of them is related to ecological invasions, when some foreign species are introduced in some area, then in some cases this foreign species can replace original species, and it begins to propagate, as is shown here in this slide. It's an invasion of American muskrat in Europe in the beginning of the 20th century, and these curves here it's real ecological data showing how this domain of the where this new species existed, how it expanded in time. Another interesting example is related to epidemic progression, and here we see another real data. So it's how the annual flu epidemic propagated in the United States from the west coast here to the east coast here, and this propagation also occurs as a reaction diffusion wave. Of course, there are many important and interesting applications in combustion, and so it was, as I mentioned, one of the first fields where the theory was developed, and this relates to combustion engines and to forest fires and to many other examples. Another important application is related to biomedical problems. In fact, many biomedical problems are described by reaction diffusion waves. Among the others, an example shown here, this is tumor growth. So here, the figure to the left, it shows different sites in the brain, these green circles, where brain tumor can appear. And this figure to the right It shows the cross-section of the tumor, again, how it develops in time. These are more or less concentric circles, and such behavior is also described by this reaction diffusion equation here shown at the top. So the next type of applications is so-called excitable medium. In particular, it is connected to brain and to heart. And here also much research was done during last, like a little bit less than 100 years. It begins from the work by Hodgkin Huxley on the propagation of nerve impulse. Then it was a lot of research done in the 1970s, in particular Belousov-Zhabotinsky reactions. Among many important applications, it's the study of cardiac tissue. You see here this figure at the bottom, how this reaction diffusion waves propagate in the heart, and in fact, they determine normal heart functioning. And if something happens with this normal wave propagation, so many possible phenomena can occur, in particular heart fibrillation, which can be dangerous. And the last application I'd like to mention, and I told you in the beginning that the theory began with the three types of applications: heat explosion, wave propagation, and pattern formation. So the third one, pattern formation, it's a very beautiful area of research, and a lot of works done in this area. And many of them I applied. I will show a little bit later, in particular to describe these patterns for animal skin and many other different patterns, and they are also described by reaction diffusion equations. So in the remaining part of my lecture, we will discuss, of course, very shortly, some simple examples related to existence of solutions of such equations, in particular to the existence of waves and pulses. So let us begin with some main definitions. So again, we have this reaction diffusion equation shown here. So traveling wave solution of this equation is a solution shown here, u of x and t equal wx minus ct. C is a constant, it's a wave speed, it is unknown, and it should be found as a solution of this problem. So if we substitute this function u of x and t in this form into this equation, so obviously we will obtain this equation shown here, second derivative of w plus cw prime plus f of w. We look for solutions with some limits at infinity, and these limits at infinity are determined in fact by this function f. So there are three main examples of this nonlinearity shown here. So the first one is called monostable, the second one is bistable, and the third one is unstable. And this classification is related to the stability of these zeros or stationary points of this equation. So we have this equation, a simple one equation, du dt equals f of u. We suppose that f of u equals 0 for u equals 0 and for u equal 1. So what we have in this case, one possible example, if this function f is positive inside this interval. So in this case, obviously, the point u equals 0 is unstable as solution of this equation, and the point u equal 1 is stable. This is why in this case it is called monostable. In the second case, these 2 points u equals 0 and u equal 1 are stable, so this is called a bistable case. And the opposite case, where both of them are unstable, then we have this unstable case. So for this scalar equation, the proof of wave existence is very simple, and I will show you how it can be done. So I recall that we have this equation W2 primes plus CW prime plus FW equals 0 with these conditions at infinity. This solution WX looks like that. It can be, for example, a decreasing function determined for all real x, and the function f is shown here corresponding to this monostable case. So this is the simplest way to prove the existence of solutions is to reduce this second order equation to two first order equations written here, W prime equal P. So then from this equation we obtain P prime equals minus CP minus FW. So this system of equations has two stationary points, 0, 0 and 1, 0, and we look for a trajectory of the system connecting these two stationary points as shown here, and this trajectory. So you see, for example, here P is W prime, so P here is negative, so corresponds to this decreasing solution. The derivative is negative. So how we can prove the existence of such solutions? So first of all, we need to study stability, the type of the stationary points, 0, 0, and 0, 1. This is a very simple analysis. Shown here, we consider this system of equations with this linearized matrix. We can easily find its eigenvalues written here, and there are several different cases here. In particular, it depends on the sign of the speed c. If c is positive, so this term is negative, then we have the square root, and under the square root, if f prime of 0 is positive and less than c square over 4, then this square root is real, and it is less than c over 2. So in this case, we have two negative eigenvalues, and we have a saddle focus. And this is for the point 0, 0, it is written here. But if we substitute point 1, 0, then f prime is negative because this is a stable point. Then if f prime is negative, so this expression under the root becomes larger than c square over 4. So in this case, we have one negative and one positive eigenvalue, so we have a saddle point. So now we return here. So this is the phase plane of the system of equations, WP. So we have this saddle point here with one trajectory going in this direction, and here we have this stable node. And then simple analysis of this system of equations show that all trajectories here at the line p equals 0 in this interval, all trajectories enter this domain under this axis. And also we can construct a straight line shown here at the bottom of this figure. Unfortunately, I don't see the cursor, so I can also only describe cannot show it, and I can also only describe it in words. So we have this straight line P equal minus KW, and under some conditions it can be shown that all trajectories are entering this domain. So the trajectory departing from this stationary point Certainly, it cannot go this way because all these trajectories are entering, and it cannot go this way. So necessarily, it goes to the this stable node, and this is true for all values of the speed, of course, under some conditions. So with a simple phase space analysis, we obtain this first theorem that monotone waves exist for all values of the speed greater than or equal to some minimal speed, C0, and if C is less than C0, such waves do not exist. So it is important to note here that we prove here the existence of monotone waves. I recall that in this case, this trajectory goes for P negative. Why it is important? Because some other trajectories, some other solutions can also exist, and these solutions are not monotone as solutions, non-monotone waves. And we'll see in the next lecture, the important difference between them is that monotone waves are stable, while these non-monotone waves are unstable. And of course, it is important for applications. So let us continue. And the second case is bistable case, where this everything remains the same, but the function f of w shown here at the top right figure, it is bistable. This point 0 is stable, point 1 is stable. So if we consider this phase plane here, then both of these stationary points are saddle points. So it is different in comparison with the previous case. So the proof also changes a little bit. So we consider this trajectory here, departing from this saddle point here to the half plane P less than 0. There is another trajectory coming here to this another stationary point 0, 0. And then it's not necessary that it is the same trajectory. In fact, we need to find some value of C for which this trajectory connects these two stationary points as shown here. But what we have at the moment, that there is one trajectory going here, another trajectory coming here, but not necessarily it is the same trajectory. So at this point, we should recall that we have this parameter C, which is not given. And the formulation of the problem is, in fact, is to find the value of C for which such trajectory exists. So now when we change the value of C, it can be shown that this trajectory and this trajectory go in opposite directions. It can be easily verified. I will not stop on that now, but if we increase the value of C, then this trajectory goes up as shown here, and this trajectory goes down as shown here, and they will intersect for a single value of C. So like that, we obtain the second result, that monotone waves exist for a single value of speed C. And this is the important difference between the monostable and bistable case, because in the first case, these waves exist for many speeds, and in the bistable, they exist only for one value of speed. Of course, all this remain true only for the simple example of the bistable nonlinearity. If we consider more complex examples, then such waves may not exist. So let us consider some examples. In population dynamics in particular, rather often they consider the nonlinearity of this form written here: a u to the power k, 1 minus u minus sigma u. So this first term describes the reproduction of some population, and the second term describes mortality of some population. And since we will return to this example later, already now, I will briefly explain. So if you take, for example, power k equal 1, so then we have this density of the population. So this, in this case, a reproduction rate is proportional to the density of the population. And this 1 minus u, it corresponds to available resources. So consumed resources are proportional to the population density. 1 is dimensionless production of resources, so this difference corresponds to available resources. So the reproduction rate is proportional to the product of this population density and available resources. This is for k equal 1, so we have this monostable case in this case. And if we consider k equal 2, power here, so in this case, the nonlinearity becomes like that. It's this bistable case, and k equal 2 corresponds to sexual reproduction when we have this reproduction rate is proportional to the second power of the population density, and k equal 1 to the first power, it's asexual reproduction. So in this example, we have this both cases, and respectively monostable and bistable with these two different results concerning the existence of reaction diffusion waves. And another very well-known example is related to combustion theory. So we see here this first term describes heat production with this exponential comes from the Arrhenius dependence of the reaction rate on temperature, and this 1 minus u this time corresponds to the limited amount of fuel participating in combustion. And the second term corresponds to heat loss. And in this case, we have also this function shown here. It is this is also the bistable nonlinearity, a little bit different in comparison with the previous one. And this form of this function with this strongly nonlinear dependence is important in combustion theory, and in particular, it allows different kind of asymptotic expansions. And what was important from the first work in combustion theory, it allowed to Zildovich and Franko-Minetsky to determine the speed of flame propagation. So the next question is the existence of pulses. So again, we begin with the definition. So we have, as before, the same reaction diffusion equation shown here, but now we consider stationary solutions of this equation. We look for a positive stationary solution of this equation having limits 0, limits at infinity. So since this is a stationary solution, we obtain this equation W second derivative plus FW equals 0. So the difference with the previous equation, we don't have this first derivative, and we have this 0 limits at infinity, and we look for this solution shown here, positive solution decaying at infinity. So as before, we can easily study the existence of such solutions. We reduce this second order equation to these two first order equations, W prime equal P, P prime equal minus f of W. And in fact, this equation can be solved even analytically, or we can study, as before, the phase plane of this system, and we can prove that under some conditions there exists such homoclinic trajectory, and this homoclinic trajectory corresponds exactly to this solution the function wx positive and decaying at infinity. And the simple analysis, which of course I don't present here, gives necessary and sufficient conditions for the existence of such solution. And in fact, if we consider this bistable nonlinearity shown here, so such solution exists if and only if this integral from 0 to 1 of this nonlinearity is positive. As before, some examples, and we consider here, we begin here with the same example in population dynamics, u power k, 1 minus u minus sigma u, with these two cases, k equal 1 monostable and k equal to bistable. And in the second case, when we have this bistable nonlinearity for k equal to, as we discussed before, so such solutions exist if the integral of this function is positive. However, and it can also be easily shown, in the monostable case, such solutions do not exist. There is another interesting example to which we will return in the last lecture, shown here. These are so-called non-local models, and I will explain later where they come from. So in fact, we have here, as before, u to the power 2, 1 minus, and instead of u, we have this integral here. In fact, this is so-called non-local consumption of resources in population dynamics. But from the formal point of view, we just consider the same equation with this already integral term. And in fact, it appears that existence of solutions in this case can also be easily studied. And what we should do is to let us, so since this integral is in fact, it is a constant. So let us call this 1 a times 1 minus integrals here at the bottom. Let us denote it by r, for example. So what we have then, we have here then this second order equation, u second derivative plus r u square minus sigma u. So its nonlinearity is like that. It is different in comparison with this previous nonlinearity. It is like that, but still it can be easily verified, even explicitly, that such equation has a solution. This solution can be, the existence can be proved, the solution can be analytically constructed, but this solution depends on this constant r. So then if we return to this relation for this constant r written here, so we have this r equal something, and this integral of the solution also depends on this constant. So in fact, what we have here, we have an equation with respect to r. This equation can be studied, and it can be shown that, in fact, we have two possible cases. It is possible that there are two different solutions shown here, two different pulses like that, or no pulses at all. And we will see later that this is important for the biological applications, because in this case, in the usual bistable case, when there is only one pulse, this pulse is always unstable. And so, of course, in applications, we are not so much interested in unstable solutions. But in this non-local case, among these two solutions, it appears that one solution is stable, another solution is unstable, and the stable solutions describe some particular type of applications in population dynamics. We will return the stability questions we'll consider in the second lecture, and then these applications to population dynamics in the third lecture. So, of course, what I showed here it's very simple results on the existence of solutions. They are applicable for the scalar equation. Even for the scalar equation, in fact, it can be much more complex. But in the multidimensional case, or for systems of equations, it becomes really essentially more complex, more involved, and only partial results exist on the existence of solutions, both for reaction diffusion waves and for pulses, and much more sophisticated methods are developed here to study these solutions. In particular, in our works, we developed some methods to prove the existence of solutions on the basis of the Leray-Schauder method, a priori estimates of solutions, and topological degree for elliptic operators in unbounded domains. So all these are quite sophisticated mathematical theories, and of course we cannot discuss it in these short lectures. And another interesting application, as I briefly mentioned, is related to non-local equations. In fact, this becomes integral differential equations, and also delay equations. I will return shortly to delay equations in the last lecture. And then in the end of this first introductory lecture, I will show you one more example exactly for this scalar equation, but multidimensional. In this case, it's a two-dimensional equation shown here, this Laplace operator. This is the same monostable nonlinearity, and these other terms appear in the applications in mathematical immunology. I also will return in more detail to these questions in the last lecture. So, and the solutions of this equation are shown here. So what we have here, we have this y variable, and we have this x variable, which goes here. So if we take this y variable, then and we forget about x variable, then we will have this stationary solution, which looks exactly like a pulse solution. So it is a stationary solution, positive with zero limits at infinity. And then if you consider this x variable, so then this pulse solution begins to propagate in this x direction. So this is a two-dimensional reaction diffusion wave between this pulse solution and this zero solution, which propagates in this x direction. And then, of course, we can do numerical simulations, and numerical simulations show some interesting behavior. In particular, what is shown here is that, in fact, there is not only one wave propagating in this x direction, but two waves. And these two waves propagate with different speeds. So you see first there is this wave, a small amplitude wave propagating with a faster speed, and then this large amplitude wave, it propagates slower. This first wave, it corresponds to the monostable case, this second wave to the bistable case, and in fact this is what is called systems of waves, when there are two or more waves propagating with different speeds. And such solutions, it's not stationary solutions, it's not reaction diffusion waves, it's something more complex, it's a combination of waves. They're quite well studied for the scale of one-dimensional equation, but for the multi-dimensional equations and for systems of equations, there are only some partial results. So to conclude this lecture, what we discussed existence of waves and pulses for the scalar equation, and this existence of these solutions can be studied by simple phase-place analysis, but for systems of equations or for multidimensional equations, these equations become much more complex, and only partial results in this case are known. So at this slide, I finish my first lecture, saying thank you very much.
Thank you, Professor Wolfert, for this fascinating lecture. And we've got a few questions for you. So what do you think about the claim of Professor Jäger, who claimed that the spread of the COVID-19 is not a diffusion phenomenon?
It's indeed an interesting question, and when he just pointed our attention to this question this morning, I was thinking about that. Yes, I completely agree. So in fact, all these phenomena are very complex, and sometimes we can describe. So we have some populations. In particular, in this particular case, we have human populations. In some cases, we can describe the motion of the individuals in this population with this diffusion equations, diffusion-like term. It's a random motion. In some other cases, we cannot do it. So it depends. It depends. You know, in former times where we lived without airplanes, so our displacement was rather short term, and probably it was more, this diffusion approximation probably was more applicable. Nowadays, like with this, all this modern ways of travel, so maybe this is less true. By the way, now, because of this epidemic, there are much less airplane travel, so maybe we will return to this previous more diffusion mode of propagation. So in this case, maybe diffusion equation will become again applicable.
All right, thank you for your answer. And the next question is it right that the heat explosion model is not covered by the 3 cases classification?
Sorry, could you repeat? There are some problems with sound.
Okay. Is it right that the heat explosion model is not covered by this 3 cases classification?
3 cases classification. Yeah, that's right, because this classification by stable, monostable, unstable. By the way, I didn't say that in the unstable case the waves do not exist. So this concerns reaction diffusion waves. But when we consider the problem of heat explosion, it is considered as a problem in a finite domain. So this classification is not exactly applicable in this case.
Okay, thank you. And the last question is, does the existence/non-existence of a wave solution depend on the behavior of the initial value function?
No, there are 2 different questions, in fact. Existence of such solutions, existence of reaction diffusion waves, and stability or convergence of these waves. So existence of solutions does not depend on the initial condition. So you may remember that what I showed in the slides, that when we substitute this function u of xt equal wx minus et, we obtain the second order ordinary differential equation. There is no initial condition. So the existence of solution does not depend on the initial condition. However, if we want to study the long-time asymptotic behavior of solutions of this time-dependent reaction diffusion equation. So our original equation is du dt equals second derivative plus f of u. If we study this equation and we consider it on the whole axis, so we need to consider the initial condition. And this is so-called Cauchy problem. So we study the behavior of this solution of this Cauchy problem, the asymptotic behavior of solutions for large time. And it appears that this asymptotic behavior is often described exactly by reaction diffusion waves. What means described by reaction diffusion waves? It means that the solution of this Cauchy problem converges to this wave solution for large time. I will return to this question tomorrow. So in this case, this convergence can indeed depend on the initial condition. It depends, of course, on the problem. For some problems, this convergence of solutions of the Cauchy problem to the reaction diffusion waves occurs for large classes of initial conditions. For other problems, this is not necessarily so, but in principle, the answer is yes. In this case, the choice of initial condition is important and it determines long-time behavior of solutions of the Cauchy problem and convergence to reaction diffusion waves.
All right, thank you again for the great lecture and your answers.
Thank you.
And now, since this was the last lecture, I would like to remind the participants that this broadcast is about to end, and after a short break at 7 p.m. Moscow time, we are having the discussion session where you will be able to communicate with the lecturers and ask questions personally. Those who want to attend, please use the link that is posted in the Q&A or find one on our website or in the program. Thank you for your attention.